بسم الله الرحمن الرحيم والصلاة والسلام على رسول الله. Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. My name is ABDESSELAM Omar. I am a student at the University of GHARDAIA, second year master. Today, inshallah, I am going to present my thesis, which is themed study and design of self-balancing robot. So the first thing we're going to start with is take a general look at our robot. So this is what our robot looks like, and it mainly consists of DC motor and a gearbox, two wheels, and a chassis, which is the body. Of course, we didn't mention the controller and the sensors, the batteries, etc., because we do not need them at the moment. At the first thing we're going to do now is model our robot. To model our robot, or by modeling our robot, I mean uh, present these mechanical systems and electrical systems in mathematical equations. All right, so the mathematical model of the robot is derived into two subsystems. Mechanical subsystem consists of the robot's body and two wheels. Actuator subsystem, which is the DC motor and the gearbox. All right, so the first thing we're going to start with is the motor, which has the input Vs, that is an electrical energy. Transforms that. The motor transforms that electrical energy into a mechanical energy, which is a rotational movement. The gearbox reduces the velocity or the speed and increases the force or the torque. The gearbox is attached to the wheels. The wheels are touching the floor, so that gives us the position or changes the position of the robot. And at the same time, the wheels are attached to the body. That gives us the tilt angle. So this is the mechanical subsystem, and this is the actuator subsystem. The first thing we're going to start modeling is the mechanical subsystem, and we are going to use the Lagrangian equation. So this is the Lagrangian equation. It has the Lagrangian L, and it has these general coordinates. What does it mean, general coordinates? General coordinates, they change from a system to another. In our case, we have two general coordinates that they are the x-axis and the tilt angle, which is theta. And this capital Qi is the general forces that are being applied on our system. In our case, they are the torque of the DC motors. And this last term is called the Rayleigh dissipation function, and it's added when we have a sliding between the wheels of the robot and the floor. In our case, we do not have a sliding, so the term is equal to 0. So general forces, general coordinates, Rayleigh dissipation. First thing we're going to start calculating is this L. This L is equal, the Lagrangian, is equal to the kinetic energy minus the potential energy. So these are the law being used. Kinetic energy is equals to half the mass times the velocity squared plus half the inertia times the angular velocity squared. So we already have the mass. We need to calculate first the velocity, and we already have the inertia. We need to calculate the angular velocity. So to calculate the velocity, we need to know the position of the robot, and from the position we can derive it, and we will have the velocity. So the position x is equal to r times phi, according to these mathematical relationships between the r and the phi, which is the angle being rotated. And the coordinates of the mass of the body, these are the coordinates of the mass of the body. X is equal to x plus L sine theta. Z is equal L times cosine theta. And to calculate the velocity of the mass of gravity, the center of gravity of the body, we derive the position, but we will get the velocity on the x-axis and the z-axis. To get the general velocity, we use the Pythagoras theorem, and we get the general velocity squared. So v squared is equal to x dot squared plus 2x dot L cosine theta theta dot plus L squared theta dot squared, and we're gonna need it later. The second thing we're gonna calculate is the kinetic energy of the body. So we put the velocity here. So that's the velocity, and we get the kinetic energy of the body. And the same, we use the same law to calculate the kinetic energy of the wheel. Now the potential energy of the body, so that's the law that we saw earlier. And finally we get the potential energy of the body is equal to mbgl cosine theta. The wheel doesn't have a potential energy because it's always touching the ground. And as I said, the Rayleigh dissipation is equal to 0 in our case. So finally, we get the after we add the kinetic energy of the body, the kinetic energy of the wheels, and the potential energy of the body and to the wheels, we have the Lagrangian formula. So this is the Lagrangian formula. Now we're going to derive it according to our coordinations. The first coordinate we have is the x. So after deriving it according to the x, we get finally this formula. And after deriving it to the theta, we get this formula. So finally, these are our two formulas after linearizing them, because our system before linearizing it was non-linear. All right. So now we move on to the actuator subsystem. The actuator subsystem has its electrical circuit and its rotor. The rotor is attached to the gearbox. So finally, we get this equation that its input is the Vs the to the motor, and we get the torque and the velocity of the wheel as the output. So by substituting the equation from the actuator subsystem into the equation from the mechanical subsystem from earlier, we get this big equation that has Vs as an input and the velocities, the angular velocities, and the angular the angular acceleration as the output. All right, now we move on to simulation. We substituted these values between brackets into uh, into into uh, into these letters because they are constants. Yes, all of these between between astaghfirullah, between brackets they are constants. So we change them with E1, E2, F1, F2, E3, E4, F3, F4, and we put phi double dot theta double dot on a side and the rest of the equation on the other side. So this is the output and Vs is the input. The input to the dynamic model of the system is the voltage Vs, and the output is the angular speed of the wheel phi dot, and the angle of the body of the robot, which is theta dot. And phi dot, we just get it from here. We integrate this and we get phi dots. Same thing goes with theta dots. All right, so these are the constants from E1 to F4. Okay, now we move on to MATLAB that we have simulated our robot or system in. So we have from E1 to E4 our constants. First of all, these are our constants or our inputs, constants being used. So we take just an example E1. So E1, this is the formula of E1 and it's being translated here in Simulink. So MB times R squared divided by 2. So that's MB times R squared divided by 2, etc. So same thing goes with E2, E3, E4, f4, etc. Now we move on to the second equation. All right, so phi double dot equals to this formula divided by A1. So that's the formula divided by A1. The Vs is the input, so that's Vs is the input. Same thing goes with theta double dot. So that's phi double dot. We derive it and we get the phi dot, which is the speed or the velocity of the wheel. Same thing we get here, the theta double dot, we derive it, we get the theta dot, and we derive it again, and we get the theta, which is the tilt of the robot. So as outputs, okay, so as outputs, we have phi dot and theta. As input, we have Vs. Okay, so phi dot, we the we integrate it again, and we get the phi, and the phi we multiply it by r, and we get the x, which is the position. So that's the kinematics. The position, we feed the position into our controller after after substituting it from the desired position, so we get the error. Same thing goes with the angle. The angle, we always want the angle to be 0, so the angle is the error. The angle is equal to the error. So now we will take a look at the controller. Controller, we started with fuzzy controller. It has 2 inputs and 1 output. So these are the membership functions of the input. This is the membership function of the output. And these are the rules relating between the output and the input. We take, for example, the last rule. If position error is positive and angle error is positive, then Vs is big positive. So that's the theta positive, and we have the x position error. The x error is positive, so we want to give we want to give plus Vs to the motor. Okay, move on. All right, so that's the fuzzy controller. So after fixing the membership functions, we get these we get these results. So this is Vs, the input to the motor, DC motors. This is the x position, and this is the theta of the robot. So we notice that the robot is following the desired position, but it's kind of slow, and it has a lot of uh, what is it called? Okay, we move on to the PID controller. So we use 2 PID controllers, one to control the position and the other one to control the angle error. So the position, we have the error position. We use the MATLAB tool PID tuner to get the values of the P and I. We didn't use D, and these are the results we got. So this is the desired position, and this is the actual position of the robot, and this is the position error. This is the tilt angle of the robot. Comparison. Now we compare between our two controllers. This is the VS, which is the input to DC motor, and this is the position of the robot. We notice that here we can see that fuzzy is in blue and PID is in red. So this is the PID. We notice that PID is much faster and smoother than the fuzzy controller. So that's the theta, or the angle of the robot, tilt angle of the robot. Realization. So how we made our robot. So this is realization. The robot has sensor to sense the angle, and it gives this sensation, or it gives this information or data to the controller. The controller, based on the data, it gives command to the actuator, and the actuator changes the environment. All right, so this is my robot, and this is its what is made of, and this is the wiring of the robot. Now we move on to a live demonstration. We're gonna see a live demonstration of my robot. I'm sorry I passed the 15 minutes. I hope it's okay. I've recorded this video over and over and it doesn't want to get less than 15 minutes. Okay, so I'm gonna pin this. All right, so this is a real-time demonstration. Okay, so our robot is trying to keep balance, is trying to stay balanced, as you can see. Yeah. All right, so that's it. Now we're going to move on to the conclusion. You can see it keeps itself balanced. All right, so the conclusion. Live demonstration. Conclusion. The objective of the thesis is the design and implementation of self-balancing two-wheeled robot. The self-balancing robot turned out to be a difficult project, and although the system seemed straightforward at first, it allowed many different techniques and concepts to be studied and illustrated, from sensing to modeling to control and implementation. First, we introduced some concepts about mobile robots and their types and gave an overview of the essential features that should be available in all mobile robots, namely autonomous navigation. The basic elements for achieving autonomous navigation are navigation, location mapping, and perception. After a comprehensive overview of the navigation of the mobile robot, a model of two-wheeled self-balancing robot was developed, as you can see here, uh, where the kinematics and the dynamics of the robot were derived in details. As we saw, we used the Lagrangian formula. The self-balancing two-wheeled robot is an example of the inverted pendulum. The robot was modeled based on the inverted pendulum. The result shows that the system is unstable without a controller. So that controller is going to fall. Uh, Two controls were used, PID and fuzzy, have been designed to control the robot based on the acquired information from a 6 degrees of freedom gyroscope, which supplies the position and the orientation of the robot. The result showed the efficiency of the designed PID compared to the designed fuzzy controller. In our case, PID was better than the fuzzy controller. The fuzzy controller can be improved maybe by adjusting its parameters, namely membership functions and the rule base. Finally, a prototype of the robot was designed and built. The robot, as you can see here, the robot is controlled by an Arduino board and equipped with a gyroscope allows it to acquire position and orientation information in order to stabilize itself. A possible direction of future work is to add an inverted pendulum to the robot to obtain a double inverted pendulum system. It means like add another degree of freedom, another pendulum on or above the robot. So that was my thesis. Thank you so much. Goodbye. Assalamu alaikum.